This is the screencast for section 5.2, example 1. We're going to start the process of being able to calculate area under the curve exactly, so not using rectangles for estimation. Now we're still going to look at some rectangle methods to get us close to that exact value. A Riemann sum was named after George Friedrich Bernhard Riemann. Basically you got your LRAM, MRAM, RAM, and those are all Riemann sums because they're constructed in a particular way by forming these rectangles. Well, now what if these rectangles, see like in 5.1, they were all the same width? What if they're now different widths? Which can happen. Also, what if there were infinitely many of them? Well, when we get to that concept, we have an integral. An integral is an antiderivative, the area under a curve from maybe from negative infinity to infinity, but could be from a to b as well. We take the limit of the sum of all of these rectangles, their heights times their widths, their limit as n approaches infinity, the number of rectangles approaches infinity, and we get this long s, which kind of means sum, from a to b of f of x dx. Now this notation down here is essentially saying the same thing, but we're saying take the magnitude of p, so the largest p you could possibly find, as that approaches 0, as that rectangle, its area approaches 0, you take the sum of those and you multiply their length times their width, and you still get that same integral notation here. So all continuous functions are integrable, and as you will see in future examples, some discontinuous functions are also integrable. But that is, if the function f is continuous on an interval a to b, then its definite integral over a to b exists. We have definitions of each of these pieces here. We have the integral sign, we have the lower limit of integration, the upper limit of integration, so a and b respectively. The function is called the integrand, and the variable of integration is the x. You have to have x's within your function and then a dx after that in order to be able to integrate, and we'll look more at that later. If you have f of a, or well, a is f of n, and then you have a dx, you wouldn't be able to take the integral. Alright, so now here's my little assessment of what an integral is step by step. Basically, in chapters 1 through 4, we looked at the derivative, which is the slope. You know that. A derivative is dy dx, and then the slope would be the limit as the change in x approaches 0 of the change in y over change in x. So we're taking the slope as these 2 points get really close together, because you can't take the slope of the same point and itself. You have to have two separate points, so we bring those 2 points together using, well, essentially the definition of derivative. Now dy dx, then, this is definition of derivative, so equals f prime, and we already know that as well. Well, now let's multiply both sides of this by dx, so dy equals f prime of x dx, so you have a differential dy. Now let's take the antiderivative of both sides, which is a very legal mathematical move. You're still making the left side equal to the right side. Well, then the antiderivative of dy is just y, and then that equals our definition of derivative or antiderivative as we stated on the previous page. So from beginning to end, our derivative equals our slope, which means the original function equals our antiderivative, or area under the curve. Now example 1 is very basic. We're just going to use the integral notation. We're going to translate from a Riemann sum to an integral notation. The interval -1 to 3, so there's your a and there's your b, is partitioned into n subintervals of equal length. Delta x equals 4 over n. So if you're using 5 subintervals, it'd be 4/5. If you're using 8 subintervals, it'd be 1/2. Basically, you have from -1 to 3 is 4 units long. So divide that into n subintervals. Let m sub k denote the midpoint of the kth subinterval. The midpoint. So we're using MRAM essentially. Express the limit as an integral. So we know we're going to start out with that integral sign. Our lower limit of integration is -1. Our upper limit of integration is 3. Our integrand is the function within side. So m sub k, those are x values. So we have 3 x squared minus 2x plus 5, and then our variable of integration there is x, so we have dx. Now be careful, you cannot write it like this. You are not taking the integral of everything, and dx doesn't apply to everything. You have to have parentheses around this function so that dx is with every term in that quadratic. Now try problem number 5 is essentially the same thing. Each c sub k is chosen from the kth subinterval of a regular partition of the indicated interval into n subintervals of length delta x. So we've got, we're going to divide this into n rectangles. Hopefully the n is going to be approaching infinity, because the more rectangles we have, the more accurate we're getting. And then we want our lower variable of integration to be 0, our upper variable of integration to be 1. Our integrand then is going to be the square root of 4 minus, now c sub k, those are the x values chosen to create our y values, so those are x squared. Those are finding our heights essentially of our rectangles if we were doing it that way. And our variable of integration is x, so we have a dx, no parentheses needed for this one because the square root groups it all together.